Math 265A, Cuesta College, I'm Joe Vasta, and today we are going to cover section 4.1. It's called Maxima and Minima. So we have a picture of a function here. It passes the vertical line test, you can see. And we should probably define what maxima and minima are. So here's our first definition. A few definitions here. An extremum is a maximum or a minimum. Maxima is the plural of maximum. Minima is the plural of minimum. And extrema is the plural of extremum. So we're getting the vocabulary down. Lots of times I'll just call them mins and maxes. But these are the official words. Let's take a look at what they want us to do with this graph. They want us to find absolute maximums. Okay? And then absolute minimum. And then some other things, and we'll get to those. So we have some numbers on the x-axis, A through B. Well, then you have some letters in between, and those are some important points on the graph. So why don't we go ahead and see what an absolute maximum is. It's a pretty simple definition. An absolute maximum, let's keep shaking, it's the highest point on the graph. That's all it is. It is also called just the maximum, without the word absolute. And then some books will call it the global maximum. We'll try to call it the absolute maximum. An absolute maximum value is the y-coordinate of the absolute maximum. An absolute maximum location is the x-coordinate of the absolute maximum. So that is what an absolute maximum is. Let's go ahead and take a look at this graph to see if we can find an absolute maximum. It really just means the highest point. Does this graph have a highest point? Well, I mean, you might think this is the highest point, but if you go over here, you see that there's points that are higher. In fact, this open circle seems to be the highest thing drawn on there. So why don't we go ahead and see what that is on the y-axis. So let's say that's 10 in terms of the altitude of that open circle. Well, we can't say that open circle is the absolute max because the absolute max has to be on the graph, and that open circle is not on the graph. So you could say, well, the highest point on the graph has altitude 9.9, and it's right here. But you can always get a point that's a little higher than that, like 9.99 or 9.99999 in terms of the altitude. So there simply is no absolute maximum. The answer to this is none. So there is no highest point on the graph. Let's take a look at the technical definition of the absolute maximum. A more technical definition is this. The point C comma f of c is an absolute maximum if f of c is greater than or equal to f of x for all x in the domain of f. So it just means its altitude is greater than or equal to any other altitude for any point on the graph. And I'm using the word altitude because it reminds you of the height. Well, the absolute minimum is pretty much the same. The absolute minimum is the lowest point on the graph. It is also called the minimum of the graph or the global minimum. An absolute minimum value is the y-coordinate of the absolute minimum. An absolute minimum location is the x-coordinate of the absolute minimum. The more technical definition is kind of like the more technical definition for absolute max. There's one for absolute min. It just says f of c is less than or equal to f of x for all x in the domain. It just means its altitude is the lowest. There could be other points on the graph that have the same altitude but no lower than that. So sometimes you can have a graph that has more than one absolute minimum. Let's take a look at our graph. So the question is there a lowest point on this graph? And we can see, if you just look at it, the lowest point is right here. Now we don't know what the y value of that point is. That the x value is s, the y value is f of s if you'd like. But what we're going to do when they ask for the absolute min or max, at least in your homework, they'll want the location. So there is an absolute min at the location of x equal s. There it is. That is the lowest point. This one's low, but it doesn't come down as low as this one right here. So there's the absolute minimum. Interior points. That's what they're asking us to do next. So let's take a look at definition here. A loose definition of an interior point. A point c, comma, f of c is an interior point of the function if the graph is defined immediately on both sides of c. Now when we say both sides, we mean to the left and to the right. A more technical definition, a point is an interior point of a function if there exists an open interval I containing c where f is defined for every point in that open interval. We'll look at the example and it will make more sense. This open interval I is sometimes called a neighborhood of C. Interior points are not endpoints. So that was quite a definition, interior points. So let's see what we have. Take a look at some interior points. This guy right here. Let's just take a look at point P. A point is an interior point of the function if the graph is defined immediately on both sides. So what I'd like to do is I'd like to put a little neighborhood up there. And do you see graph on both sides? Yes, I can make my neighborhood as small as I like, but it has to have both sides of the point, and you see graph on both sides of the point. And so we'd say point P is an interior point. In fact, this point right here, which was not actually labeled on the x-axis, that's an interior point because there's graph on both sides. So all these points are interior points, but you got to say that A is not an interior point because it does not have graph defined on the left side of it. You see, so it only comes from the right side. On the left side there's no graph, so A is not an interior point. And in that definition it says interior points are not endpoints. So our interior points happen to be anything to the right of A. All those points are interior points. Now, is T an interior point? The answer is yes, because T has function defined on both sides. It doesn't matter, you know, like we can make the neighborhood really small. It has function on both sides. It's defined on the right and it's also defined on the left, which is up there. So T is an interior point, and so is point U. So the interior points go all the way from A, not including A, to B, not including B because B is an endpoint. So to describe the interior points, we would just use the interval A to B. So those are what interior points are. Let's go ahead and do another definition, because what are they asking us next to do? They're asking us for the local maximum. So here is the definition of a local maximum. The first definition is the one that's going to be the easiest to think of. A local maximum is the highest interior point within a given neighborhood of the point. It is also called a relative maximum. So we can define a local maximum value as the y-coordinate and the location is the x-coordinate. A more technical definition, and you could just ignore this. The interior point C, f of C is a local maximum if f of C is greater than or equal to f of x for all x near C on both sides. So basically a local maximum has to be the top dog in his neighborhood. Okay, so what does that mean? Well, remember point P here? You know, we'll call this point P, it's the location. He was not the top dog of the whole graph. There were points that were higher altitude than this guy. But if you put a neighborhood around him, look at that. He looks like the top of a hill, doesn't he? And so that is what it is. A local maximum is the highest interior point within a given neighborhood of the point. And he is the top dog of that neighborhood. He's even the top dog of that neighborhood as well. He is the highest point. So when they ask us to list the local max, they're going to actually ask for the local max locations in these problems. So I'll say at, and we better put point P. Okay, so let's look at the graph and see if we see any other tops of hills. So we come down here. Well, right there looks like the top of a hill, and we could put a neighborhood around that. And he is the top dog in that neighborhood, so we better add R to the list. Do we see any other hilltops? Well, that's not a hilltop there. And that's not a hilltop. And it looks like we can't do anything else. Now, looks like we're done. Our local maxes, I should say local maxima, our local maxes, they're located at P and R. Okay, so right there, those tops. So we have that right there. Okay, so I think what I wanted to avoid doing on this problem, I wanted to avoid having a horizontal line. Yeah, I'm going to do that for a reason here. So I'm going to go ahead, a horizontal line segment. I'll make it go like that. Okay. We'll talk about that before we move on to our first problems, our other problems. Okay, so look what we have. We have our local maxes are at P and R. Okay, now I did that on purpose because some people would want to say, well, let's go ahead and make B be part of this list here because it looks like a local max. The reason we can't do that is because we'll go back to the definition. It says a local max is a highest interior point. So n points cannot be local mins or maxes. So this guy right here is an n point. He is not on the list. Okay. Local mins. So those are the bottom of the valleys. Locally. So a local min is the lowest interior point within a given neighborhood of a point. It is also called a relative minimum, and then you have the value and the location. There's the more technical definition, which I'm not going to go over. So do we see any bottoms of valleys? Well, we see something right here, and that, you know, reminds us of a minimum, but because it's not an interior point, because it doesn't have a neighborhood on both sides, we cannot call that a local min. Okay, it's kind of a bummer for that one, for that point there. So do we see any bottoms of valleys? Yes, we do. Right here at Q. Q is, and I'm going to use the expression bottom dog, you know, as opposed to top dog. He's the bottom dog of his neighborhood. There's no one else lower than him. Yes, now if you look at the whole graph, there is. That guy's lower. But if you just take a neighborhood around Q, sufficiently small neighborhood, he is the minimum of that little neighborhood. So we're going to put him in this list. So we have a local min at Q. Where else do we have one? Oh, look, we have one right there. Okay, so looking at this, we have another bottom of the valley right here at S. So we have one at Q, we have one at S. Now let's take a look at these points because we really have to explore them a little more. Is this point at T a local min? And the answer is no. He is not the bottom dog of the neighborhood. Okay. So we do not have a local min or a local max at T. Let's take a look at this guy right here. We'll put a neighborhood around him. Point U, we'll call it point U. Is he the bottom dog of his neighborhood? Is he the lowest point? You look on both sides? Yes, he is. So U is going to go in the list. So we have a local min at Q, at S, and at U. And I think we should put Q like right before U because, I don't know, I'm trying to remember grammar. Don't you have to go QU? Oh well, maybe not. Okay, so that was my attempt at trying to be funny, and it's not going to happen, guys. So there it is, our local mins and our local maxes. They are the tops of hills and the bottoms of valleys. Let's take a look at this. Now we know about a local extrema. When a bug turns around on the number line, so if you're doing the bug example, then that creates a local extremum on the graph of S. So when the bug turns, so if this were the graph of a position function of a bug on the number line, when that bug turns around, then it gives you a local min or a max. And so we know the bug's turning around there and there and there and there. This is a bad example for the bug on the number line because we have this jump right here, and it would be like the bug would have to disappear and appear somewhere else on the number line, and then same here. Okay, the last thing that they're actually looking for in this is critical points. So if I have this definition here, I do. So what are critical points? So this is going to be very important in our homework. A critical point F is an interior point C, f of C in the domain of F such that f prime of C equals 0 or f prime of C does not exist. Your book calls C the critical point, and it's just the x value. Other books will call C the critical number. So know that some books call those things different things. Let's take a look at critical points here. So critical points are interior points, so there are points within AB such that the derivative is 0 or the derivative does not exist. Let's look at where the derivative is 0. The derivative is 0, that would happen to be where the slope, let's look at the slope right there, is horizontal. And the places where the slope is horizontal happens to be right up there. So right where we had this guy right here, P. So one of the critical points happens to be at point P. Now we have another one. Here's a minimum right here at S. That's when the slope is 0, so we have another one at S. I'll put a little space for a reason. Should have made the space larger. Okay, look right here. This point right here, it is a local minimum, but it's a corner on the graph. And remember what we said about corners, the function is not differentiable, or the derivative does not exist right there, because maybe from the right hand side it looks like it's 1 or 2, and from the left hand side it's negative. So the derivative is undefined or does not exist at Q. Q's an interior point, so we're going to put that on the list. We have another corner up there at R. Okay. The derivative of this graph does not exist at T, and T is an interior point because it has graph on both sides. So there's a critical point of T, and then also it's discontinuous at U as well. So here's our critical points. P, Q, R, S, T, U. It's pretty much all those are critical points. Now the critical points, because they are interior points, cannot be the endpoints A and B. They have to come from this interval. So we have that right there. So we have a theorem that says the following. It says, if F has a local maximum or local minimum at C, then C is a critical point. Okay. So if F has a local min or local max, then it is a critical point. So look at these. All it means is you will see these guys right here. Your local max is a critical point. Here's another local max at R. It's a critical point. And your local mins, Q, S, and U, Q, S, and U, those are critical points as well. So local mins and maxes are critical points, but not all critical points are local mins and maxes. Here's a critical point right here. Point T, which is not a min or a max. So if it's a local extrema or extremum, then it's a critical point. But the other way around, the converse of that theorem is not necessarily true. The converse is if it is a critical point, then it is a local extremum. That is a false statement. And so notice this theorem has if then. If local min or max, then it's a critical point. And that's going to be important in chapter 4. So this pretty much covers our first example. They'll ask you in your homework, they'll give you a graph and they'll ask you the locations of the absolute max and absolute mins and the locations of the local max and local mins. Critical points, which you'll just put the x values, and we have to know what interior points are. So let's move on to our next example. So for some of you, you might want to skip over this example here. I have to tell you why I whited out the horizontal line. You're not going to have anything this complicated in your homework, but it's worth seeing if you're interested in math. So this graph here, we call it G, has an absolute max at C. That's really not, I mean, oh sure, I'll write that. Absolute max at C. The absolute min on this graph, absolute min, it just keeps going down. So there is no lowest point. The absolute min is none. We could talk about the interior points and the critical points, but really what I want to talk about on this graph is the location of local max. Okay, so local max location. So is there a local max? And you might say, oh, well, there's not. I don't see the top of a hill. Well, let's go ahead and take a look at this neighborhood right here around A. And look, is A the top dog in his neighborhood? And you might say, no, he's not. Well, remember the definition of a local maximum. It's the highest interior point within a given neighborhood of the point. If you look at the more technical definition, it says you've got this local maximum at C, and it says f of C is greater than or equal to f of x for all x near C on both sides. So here's all the points on both sides. Is there any point that is higher than this point right here? No. Now some of them tie in terms of altitude. They're the same altitude as this point right here. So this point, which is point A, shares the top dog name with these guys over here on this horizontal part. So A really is a local max. The part that you're not going to like is just pick any point within that horizontal part. That guy right there, okay, he doesn't have a label on the x-axis. We can just call him D. D is also a local max because there's no one in that little neighborhood that's above him. He's the top dog. Yeah, he shares that title with all those other people in the neighborhood, but he's still a top dog. So the weird thing about horizontal lines is that this guy is a local max, but so are all of these guys right here. Those are all local maxes. Now, is there a local max at B? No. B happens to be something that is not the top dog. It doesn't matter how small you make that neighborhood, he's never going to be top dog, because you always have to have a little bit of neighborhood to the right of B. And so your local max locations would actually be from A, including A, to B, not including B. So there's interval notation there. And your local min locations, well, now we would see that point A would never be a local min. It doesn't matter how small you make that neighborhood, there's always going to be someone below him in that neighborhood. So A would never be a local min location. But anything to the right of A on that straight line, even this point right here, will be a local min, because you can make the neighborhood small enough where he will be bottom dog. So the local min locations would go from A to B, including B, because now if you look at B, B happens to be a local minimum. So we wanted to get into this example here to show you that horizontal lines are kind of weird when it comes to local mins and maxes, but it's not something you'll see in the homework. Let's move on to the next example. What is this? Find the critical points. This is what we are doing in our homework. The critical points, once again, it's where the derivative is 0 or the derivative does not exist. Let's go ahead and compute the derivative. So the derivative is 3x squared minus 12 plus 0. So to find the critical points of something like this, we set it equal to 0. Now this guy's defined everywhere for all real numbers, so we're only going to set this thing equal to 0, and that's how we're going to find these critical points. So I have 3x squared equals 12. X squared equals 4. There's something called the square root property, where you take the square root on both sides, and the side with the number you put the plus or minus. So this gives me x equals plus or minus 2. My critical, now look, I have points in quotes because, you know, these really in other textbooks are called the critical numbers. But anyway, we'll call them critical points. They happen to be plus or minus 2. So now this graph here, so we're done with the problem, and what I'm going to do now is just for all the math majors and maybe, you know, engineers, I don't know. I'm going to graph this graph. Now if I were in class, I would graph this graph on a, you know, Desmos. In fact, that's what I did. I graphed this on Desmos, and I'm going to show you the results. Remember, the critical numbers are plus or minus 2. There's the graph. What do you notice? Well, there's a local max at x equals -2. It's right there. And a local min at x equals 2. And so those critical points happen to give me, they happen to be local mins and local maxes of the graph. Let's go ahead and do another one now. This one's a little bit trickier because it has a fraction. So the directions, I'm not going to write the directions on every sheet. Find the critical points. I'm going to go ahead and take the derivative. So why don't you pause it, take the derivative, and maybe you can even try to figure out how to find the critical points. There's a bit of a sun. There we go. There are some sunspots there. I had to go get an oar from the garage, and I'm propping it kind of against the window so that does not have the sunspots. Actually, that probably did not make sense to you. So I'm going to move on and find the derivative. I'm going to do the quotient rule. The quotient rule says the derivative of the top times the bottom minus the top times the derivative of the bottom. This is all over the bottom squared. Okay, so I'm going to go simplify the top. This is 2x squared plus 2x minus x squared all over the bottom. And so on the top we have x squared plus 2x. This is all over the bottom. Okay, so we have x plus 1 squared. And you know what I'll do just to make it look good? I'll factor an x out of the top, though that is unnecessary. So I have x plus 2. This is all over the bottom squared. So how do I find the critical numbers? I set the top equal to 0. Hold on here. Set the top equal to 0. And I end up getting x equals 0, x equals negative 2. And then I set the bottom equal to 0. And I'm going to end up getting x equals negative 1. Now, I want to check to make sure all three of these happen to be in the domain. So the critical points have to be in the domain. And the domain of this is all real numbers except negative 1. So this guy right here is not in the domain of f. So he is not going to be a critical number. So the critical numbers are going to be 0 and negative 2. And so that completes problem number 2. If you want to see the graph on it, I'll go ahead and show the graph. By the way, that's a 0 and that's a tick mark negative 2. The graph looks like this. You actually have a local max at x equals negative 2 and a local min at x equals 0. And it actually touches the origin there. And there is a vertical asymptote, if you care, at x equals negative 1. That's the domain. Exclude it, x equals negative 1. Let's go ahead and do the next problem. Find the critical points. So go ahead and perhaps pause the video and see if you can do this problem. Okay, I have the derivative. This here is the product rule. The derivative of the first times the second plus the first times the derivative of the second. Okay. So I'm going to go ahead and factor out an e to the x, and this is going to give me 1 plus x. So there is no denominator here like there was in the last problem, and the domain on this is all real numbers, so I don't have to worry about perhaps throwing something away. I'm going to set this equal to 0. E to the x equals 0. 1 plus x equals 0. So this one gives me x equals negative 1. And this one, there's two ways of looking at this. Y equals e to the x is this graph that looks like this, an airplane taken off, it's the exponential graph, will that ever have a value of 0? Will it ever touch the x-axis? And the answer is no. The other way to do this is to ln both sides of this equation. And of course the left-hand side is going to say x equals, but the ln of 0 is undefined. So this is a dead end. Dead end. And so our critical point is -1. Critical number is -1. And if we do the graph of this, now you don't have to do the graphs in your homework. I just did this on a computer. At -1, what do we see? We see a local min. Okay. Let's go ahead and do another example. This example right here is f of x equals x minus 1 times the square root of x. So really we want to write this as x minus 1 times x to the 1/2 power. I'm going to go ahead and do the product rule. The product rule says the derivative of the first times the second plus the first times the derivative of the second. So I could have very easily multiplied that through and got x to the 3/2 minus x to the 1/2 and done this problem without the product rule. But oh well, now I've done the product rule, so look what I have. I have x to the 1/2. I can't decide how to write my fractions. Look at this, I'm going all crazy. Okay, well anyway. Then we have on the top x minus 1. This is going to be a fraction. It has a 2 on the bottom, and cross the line, change the sign, so I have x to the 1/2 on the bottom. Those x to the 1/2 are really square root of x, if you like to put them like that. So this is 2 root x. I'm going to get a common denominator and put those together, and this is going to help me find the critical numbers. So the common denominator is 2 root x, so I'll put a 2 here and a root x there. So on the top of my fraction I have 2x plus x minus 1, and on the bottom of the fraction I have 2 root x. Okay, so this gives me 3x minus 1 all over 2 root x. You set the top equal to 0, you get x equals 1/3. You set the bottom equal to 0, you divide by 2 and square both sides, you'll get x equals 0. So it looks like we have two numbers here. The domain for this happens to be all real numbers greater than 0. This is the domain of f. Okay, it's because of that square root. So as much as I want to put 0 and 1/3 for my answers, critical numbers, if you look back at the definition, critical points are interior points, and this guy is on the frontier. We never use that word, but that's a word some math teachers will say. He's on the frontier or on the boundary. So this guy is not interior. And so that means we have to throw that guy away. I know it's kind of sad. And we just have one critical number. It's 1/3. Let's go ahead and check the graph on this. Look at the graph. That's a weird graph of x minus 1 square root of x. It starts like this, right at 0, 0. So that is the boundary point. So it's not going to be a critical point. But the critical point was at x equals 1/3, and it's a minimum, local min. Let's go ahead and do another problem. So we'll take a look at this. It almost seems like every time we get a critical point,
or we're looking for critical points and we set the bottom equal to 0, we always have to throw it away. Let's see if that's always going to be the case. Maybe you can pause and do this on your own. Okay, here it goes. The derivative of our function is, I'm going to do the chain rule, 2/3 x minus 1, and then we go 2/3 minus 1 is -1/3. We're going to multiply that by the derivative of the inside, which is 1. So what this gives me is 2 on the top and 3 x minus 1 to the 1/3 on the bottom. By the way, the domain on this guy, like if you're wondering, the domain happens to be this, x minus 1, and this guy could be written like this, the cube root. You can take the cube root of any real number, so the domain is all real numbers. Which also means there's no boundary points. That means all the points are interior. Okay, this is what we have here. If you want, now this is optional, you can write the derivative like this, 3 cube root of x minus 1 on the bottom. Well, the bottom line is when you have the derivative and it looks like a rational, well, this is not a rational function, when it looks like a fraction, you set the top equal to 0. Well, that's a dead end. And you set the bottom equal to 0. 3, that's weird, the cube root of x minus 1 equals 0. I'm going to divide both sides by 3. I'm going to cube both sides. What does that look like? If you're wondering, it looks like that. X minus 1 equals 0. And then I'm going to go ahead and add 1. So find the critical points. We found 1. It's not a boundary point. It's an interior point. So we have 1 for our answer. And if you actually look at this graph, I think this one's kind of cool. There is a local min at x equals 1. And there's a cusp right there. And it has a vertical tangent, which is weird because look at the tangent right here. Maybe I should use the nail file. I don't know. I had a sharp point right there. Okay. So look, as you follow the tangents, the tangent becomes vertical there, and coming from this side, it becomes vertical. It's undefined slope. But it's interesting because 1 still is a local min, even though it's not differentiable at that point. Okay, once again, graphs optional. Let's go do our last problem. And you'll probably be surprised at problem number 6, the fact that it looks like something that's not so challenging. So let's just do this anyway because we want to illustrate something here. F prime equals 3x squared. To find the critical points, you set that equal to 0. The domain is all real numbers, so the critical point is 0. That's the answer for that. Now, here's the deal. That's what the graph looks like. And I kind of put a 0 there. That's a 0. It's not an open circle. I don't know why I wanted to emphasize that. But this looks weird. 0, 0 is not a local min or a max. So this is an example of where we have some critical points that are not mins and maxes. And so we can come back to this theorem here. It says, if f has a local min or max at C, then C is a critical point. So I have a Venn diagram where I'll say, here are critical points, and inside this I have local mins and maxes. And so that is what we have here. So what we're going to do now is look at our last theorem. So the converse is not the same. Okay, so this right here is a Venn diagram. And you know, we can go like this. Here is another Venn diagram of cats. And inside here we have kittens. And the theorem says, if you are a kitten, then you're a cat. If you are a local max or min, then you're a critical point. But the converse is not true. If you're a cat, then you're a kitten is not true, and the converse of this is not true as well. So let us go ahead and look at our last theorem. It's called the extreme value theorem. If f is continuous on a closed interval AB, then f has an absolute maximum or minimum on that closed interval AB. So the last grouping of problems in your homework, they're going to give you a function in a closed interval, and they're going to ask you to find absolute maximums and minimums. And I'm saying that wrong. I should say maxima and minima. So that is what we'll do. Okay, so let's go ahead and use the extreme value theorem to do these problems here. Okay, so problems you'll see that are like your homework problems would be determine the location and value of the absolute extreme values of f on the given interval, if they exist. So if I were writing the book, I would just say determine the location and value of the absolute extrema. I wouldn't say the values, but I mean, this is good enough. We'll see what we can do with this. So what we're going to do is, there is a method, and you can look in your book. There's a method of finding the absolute min and the absolute max of a function that is continuous on this closed interval, and this function is continuous on that closed interval. And the method is find the critical numbers first. So that's what I'm going to do. How do I find the critical numbers? I take the derivative. So this is 3x squared minus 12x plus 9. So I take the derivative, set it equal to 0. Okay, so I'm solving this equation here. So here's the equation I'm solving. And I'm going to divide everything in that equation by 3. So I have x squared minus 4x plus 3 equals 0. I'm going to factor this. So this is x, 3, and 1. Put some negatives there. And looks like I get some critical numbers of 3 and 1. Okay. The next thing we're going to do to find the absolute min and the absolute max is make a list. So go ahead and put these in order, and I'm going to put them vertical. So this is -1, and then I'm going to put 4 at the bottom, and any critical numbers that fall within those. So yes, we're going to have to check 1 and 3. So to find absolute extreme values, you plug those in to the function. Okay, so this is just, and this is plugging it into the original function. So you plug -1 in there, you get -1 minus 6 minus 9, so that's -16, and then we have plus 2. So this is -14, and you plug 1 into this. So you end up getting 1 minus 6 plus 9, so that's 4, 5, 6. I should be using a calculator perhaps. I plug 3 in here, so I end up getting 3 times 3 is 9, 27, 27 minus, and then we have 3 squared, that's 9 times 6, 54, but then we have plus 27 plus 2. I believe we are going to get a 2 on that. Okay, so what happened, f of 3, if you're wondering what happened. That was 27 minus 9 times 6, so minus 54 plus 27 plus 2. And these guys, 27 plus 27 is 54. So yeah, there it is. And f of 4 is going to be even more traumatic. 64 minus 6 times 16 plus 9 times 4 plus 2. I ended up getting 6 on that one. So what they're asking for is, in this interval, what is the highest? What's the highest point and the highest value? These are values here. The highest value is 6. So the absolute max value equals 6. And the location, because they want the location and the value, I put the value first. At x equals 1 and 4. And then the absolute minimum value is, so what's the minimum value of these 4 numbers? The minimum is negative 14. There's only one location that happened at, and that's at x equals negative 1. So that's pretty much what they want you to do in your homework when they ask you to determine the location and value of the absolute extreme values. And once again, the extreme value theorem says if f is continuous on a closed interval, then f has an absolute maximum or minimum. This actually should say, and okay, we have an absolute max and an absolute min. Now, what does this look like? I went ahead and graphed this in Desmos, and I actually went ahead and used a Sharpie to put the graph that's on here, and this is what I got. So remember our results there. Let me go ahead and, you know what, I'll fold this here so we can see it and see this result there. And so look what I have here. I have an absolute max. So the absolute max, there's actually a tiebreaker. Those are both the top dogs. One's at 1 on the x-axis, that's 1, and then another one is, location is 4, and they have the absolute max value. I know that says 5 there, but they're a little higher. It's 6. And the absolute min value happens to be negative 14, and that happens at x equals negative 1. The picture is optional. You don't need to do the picture when you do this. And our next problem, now this is weird that I'm doing this, is pretty much the same problem. And the reason I'm doing this is because we've found a lot of critical numbers today. Ooh, there's that sunlight. It's now shifting. Move my oar. Uh-oh. Ooh, yeah, perfect. So the only thing I've done was change the intervals. So I had some critical numbers. Critical numbers, or your book calls them critical points, and they were where? They were 1 and 3. So what I'm going to do is I'm going to kind of do the same thing I did here, where I write 2 and 5. And do I have any critical numbers that are in between those? There's only one that's in between them. It's this guy right here. It's 3. And I'm going to go ahead. So you might think I gypped you off. I'll do another problem after this because we've already found the critical numbers. There's only one critical number that falls within that interval. So this one, it doesn't matter, and then I'm going to go ahead and see who wins this contest. Who's going to be the top dog? Who's going to be the bottom dog? And maybe there will be another tie. We've already computed f of 3. F of 3 happened to be 2. So let's go see what these guys are. F of 2 is going to be 8 minus... Wait, didn't we already do f of 2? No, we didn't. Okay, sorry about that. I got a little confused. So f of 2, yeah, so you just plug 2 in there. And when I plug 2 in there, I got the value of 4. And when I plugged 5 in there, you know, probably right now we're using our calculator, I ended up getting 22. So who's the low? The low is this guy right here. That's the bottom dog. He gets a little ribbon for that. And then the top dog, we'll just say the high, is 22. So how are we going to write our answer? We're going to write our answer the same way. We're going to say the absolute, this graph has an absolute max value, and that equals 22 at x equals 5. And then we have an absolute min value equals 2 at x equals 3. So there it is. Now this kind of stuff reminds me of when I took game theory and people try to optimize strategies on games, and there's a region, and you use this theorem that we've been using, the extreme value theorem, to figure out the best strategy when you're playing a game. So there is a branch of math called game theory where this is implemented, and it's not just people who like games who take a game theory class. People in the business world will often find game theory helpful because it helps them maximize their profits and their strategies you use in business, and it all comes back to calculus. What does this graph look like? So it's the same graph that I had last time. So remember, the last graph I had was this, and now this graph right here, I'm going to go ahead and fold this so we can see everything, looks like that. So that critical value that I had last time, which was at 1, is not used because it's not within the interval. The interval goes from 2 to 5, and look, the maximum value, so the maximum point is 5, 22, which is right there, and the minimum, the absolute minimum point in this interval happens to be right here at 3, 2. Yeah, so I think what's freaking me out is I didn't label this one right here 3. I don't have the purple pin. And so the picture kind of shows us exactly the results that we got. Okay, so we'll take all this and go ahead and do this last official problem. Go ahead and find, what are the instructions? The instructions are determine the location and value of the absolute extreme values, if they exist. Okay, so what are we doing here? This is on a closed interval. The first thing we want to do is we want to take the derivative. So because there's some trigonometry here, if you're standing up, you might want to sit down because of the shock value. The derivative of the sine is the cosine, and the derivative of negative 1/2 x is minus 1/2. So I'm going to take this derivative, set it equal to 0. This gives me the cosine of x equals 1/2. Now how do we deal with that? Well, what I do is I go ahead and I draw a triangle. I don't know what size it's going to be yet, and I'll put an x there. And Oscar had a hunk of apple, so let's see, cosine is adjacent over hypotenuse, so this is the square root of 3, which makes my x 60 degrees. Okay, now we're going to change this to radians for our answer. And this is a positive 1/2, so now some of you might be using the unit circle on this, but I don't use the unit circle. So this is 60 degrees right here. All students take calculus, which is a lie. This tells you that the other quadrant that cosine is positive is down here. So this right here will be the other one, which gives me 300 degrees. Now really I should be saying, oh look, I'm going to go 60 degrees plus n times 360. But I'm only doing this in this interval from 0 to pi. So from 0 to pi, that's 0 to 180. The only one that I'm going to consider is 60 degrees. 300's out, and 60 degrees plus 360, that's out as well because it's not in that interval. I'm going to change things to radians, so remember how to change this to radians. I know some of you would just use your calculator and that, maybe that's all right. Pi over 180, and so that's 6 over 18, which is 1 over 3, so this is pi thirds. And really, I mean, a lot of you may have already just memorized that. So pi thirds is a critical number. So what I'm going to do, pi thirds does fall in there, and I'm going to make my list here. 0, pi thirds, and pi. And I'm going to stick each of those into the function. Now here's the deal. This function, the original function, this is what I'm looking at, has this x here, but it also has an x here. So what I've done, what I'm going to do is just plug this into my calculator. The first one I don't need the calculator for. Sine of 0 is 0, and then this, so the first one gives me 0. So we don't know who's going to be the top dog, who's going to be the bottom dog. It's a contest. We'll give out ribbons at the end. When I put pi thirds into my calculator, make sure your calculator is in radians. You do not want to plug degrees in here because you'll just have a mix of units, which is bad. So use radians, and I ended up getting approximately 0.34 for that. And the other one, pi, when I put that in there, sine of pi, it's pi, negative pi, so I ended up getting negative 1.57. Now these are approximates, so let me curve those equal signs to say that kind of shows you that I kind of round it. And which one is the top dog here? Which one is the high? Well, let's just say top dog now. The top dog is going to be the highest number we see here, which is this guy right here. So this is the top dog. And the bottom dog, or the low, is this guy right here. So how are we going to write our answers? We're going to write our answers like we've been writing our answers. The absolute max value in that interval is approximately 0.34, and this happens at x equals pi thirds, and the absolute min value is approximately negative 1.57, and this occurs at x equals pi. So we're done with this problem. What I'm going to show now is just a little visual satisfaction with this, so you can see what did we find. Here's the graph. We found this. The minimum happens at pi. Let's say it happens at pi negative 1.57. There's the minimum. And the maximum value, which is this guy. So if you look at what's the highest point on this dark graph that I have, because this is between 0 and pi, it happens to be pi over 3, comma, 0.34. So hopefully the graph matches with our answer. And we'll move on. Now this is the time where some of you can turn off the video, because what I'm going to say now might go above and beyond what you'll see in your homework. But if you want to keep this on, it might help understand some things as well. I'm surprised your book didn't give problems like this. I'm just going to go ahead and do this. I'm going to ask you, what is the absolute max of this graph? Is there a highest point on the graph? And the highest point is right there. Okay, so we're looking at from A to B, and the highest point is at x equals A. Now, what is the lowest point on this graph? Well, look at this. There's a vertical asymptote there, and the graph just keeps going lower and lower and lower and lower, so the absolute min none. The local max, let's look to see if there's any local maxes. It can't be this because local maxes cannot be endpoints. They have to be interior points. Local max, we don't have a local max. That doesn't look like a local max. Look right here. Looks like there's a local max at x equals r, because look, he's kind of at the top of that hill. X equals r. And the local mins happen to be, well, let's see where local min is. Do we see any local mins? Well, Q, that looks like it's the bottom, it kind of looks like the bottom of the valley. The valley is flat there. Let's just throw Q in here. And here's another one. Look at this. Put a little neighborhood around there. This guy right here, this point, is a local min, because he has graph on both sides of him, and he is the bottom dog. So P is also a local min. Now here's the part that's going to frustrate some of you. Our answers here are not totally correct. In terms of just these points, yes they are, but the local maxes happen to be infinitely many local maxes. Now why is that the case? Well, let's just take a point right here. Put a neighborhood around that point, and he's not labeled on the x-axis, but you could see that point there. Is he the top dog of his neighborhood? And you might say, oh, well, no, he's not, but is there anybody who has a higher value than him? Is there anybody who's higher than he is in altitude? No. So he is the top dog of his neighborhood. If you go back to the definition, I don't even know if I can find the definition. Here it is. It says, what are we looking at? Local, am I looking at local maxes? I think I am. Yeah, let's take a look at the local max. It's the highest interior point within a given neighborhood of the point. But look at this, a more technical definition. It says the point is a local maximum if it is f of c is greater than or equal to f of x for all x in that neighborhood. And so it happens to be equal to all the other values of the x's in that neighborhood, which it's allowed for in the definition. So they're not going to give you anything this bad in your homework, but I would say then that there's infinitely many local maxes, and they're right here. So your local maxes, I'm going to cross that out, they happen to start at Q and go to R. Now, we did say R is the top dog of its neighborhood, and he is. Okay, so he ties with some of the other people. But is Q the top dog of his neighborhood? Is Q the highest value? Is that point the highest value in the neighborhood? No, so we're going to put parenthesis there. Once again, let me remind you, when you're doing your homework, you do not get anything this bad. Now let's look at the local mins. The local mins, yes, we do have a local min at P. Right there, because he's the bottom dog in the neighborhood. But all those guys right here, that point right there, who we said was a local max, he's also a local min because he's the bottom dog in his neighborhood. Yes, there's a tie between all those people in his neighborhood, so all these points right here are local mins. And so we're going to say from Q to R. Now here's the deal. Is Q a local min? Yes, it is. It's the bottom dog, so I'm going to put bracket. Is R a local min? So any neighborhood, you make it as small as you can, as long as you have an open interval around R. R is not the bottom dog. So I'm going to put parenthesis. But the point like right next to R, he is the bottom dog because you can make, this point right here is the bottom dog because you can make the neighborhood sufficiently small and say he is. But R will never be the bottom dog, and that's why he's not included. So once again, this was bonus. You don't have to pay extra for this. And that takes care of this section.